We start with the example of a pendulum which is pulled back to some angle theta. Got a mass m, we assume a light massless rod or string. Length is L. Swings back to equilibrium. We want to look at the energy exchange. So the gravitational potential energy decreases. Everybody told me, yeah, it decreases. Didn't ask why, but the instinct is that it decreases. The thing goes lower. If you release something from a higher point and nothing interferes, it's going to go lower and pick up kinetic energy. Okay, what's the distance of descent? Okay, because we want to get a handle on the gravitational potential energy situation. To calculate the potential energy change, we have to know the work gravity does on the object, essentially, because the work gravity does on the object is equal and opposite to the change in potential energy. That's because if the potential energy decreases, the kinetic energy increases due to the work done by the conservative force that's causing the potential energy decrease. So anyhow, the distance of descent here is, well, from this point to this point. Now we had a little trouble getting a handle on it, so I said, well, okay, let's think about this light purple right triangle here. As somebody did identify that we have a right triangle. So what does the right triangle tell us? Well, you might not know what it tells us about this. You might not have gotten that far in your thinking, but at least you can analyze this right triangle. You know the angle, and you know one of its sides, and you know it's a right triangle. So here it is, and people were pretty slow at seeing this, so that concerns me a little, and my advice is you really have to understand right triangles very well immediately, okay? Anyhow, here it is. Angle here is theta, here's L. This side is adjacent to the angle, so that's L cosine theta. This side is opposite the angle, that's L sine theta. So, I ask which side is directly relevant to the change in potential energy. And I think everybody told me you had choice A or B, that it was choice A, so that's pretty good. Change in potential energy now is the definition I use, which is totally consistent with the definition your book uses, is that it's equal and opposite to the work done on mass by gravity. Now, that's not a general definition of potential energy. The general definition is equal and opposite to the work done by conservative forces. So I'll say potential energy gravitational. Not sure that came out very well, but that's GRAV subscript. Okay? Well, what's the work done by gravity? It's the force exerted by gravity multiplied by the change in your vertical position. Now we can do this, and I chose to do this with vectors. What's the force of gravity? Well, it's negative mg times j if we use coordinate system that's what the book calls level. The x-axis is horizontal. The change in y, well, we still don't have the change in y, but if we look at the picture now, we know that this distance here is now L cosine theta. So, from here down to here, we could represent with a vector of length L cosine theta, and that vector I say is negative quantity L cosine theta times the j vector. That's this vector. Okay? Vector from here down to here is negative L times j, because the length of the pendulum is L, that's going to be this distance. So then the question is, what's this? And this vector represents the change in the y-coordinate. Well, obviously, this plus this equals this, so this must be this minus this. And we conclude that the change in y is, and you can work out the details, but if you do negative Lj minus L cosine theta, it'll be the negative of L minus L cosine theta quantity times j. So the work that gravity does on the system, being the dot product of the force with the displacement, is this. Okay, so here's our expression, mg times the quantity L minus L cosine theta. That's the work gravity does on the system. So, another way intuitively, the mass mg drops the distance L minus L cosine theta. Gravity does work, same expression, mg times the quantity L minus L cosine theta. So potential energy change is the negative of that, equal and opposite to the work done by the conservative force. And that's this expression, and we distribute the negative through, and, well, I didn't distribute the negative, but I factored the L out here. I got negative mgl times the quantity 1 minus cosine theta. Now, if no forces other than gravity act in the direction of motion, we pose the question, what is the kinetic energy at equilibrium? Well, if there are no forces other than gravity acting in the direction of motion, and there are forces other than gravity. There's the other force basically is the tension in this string or rod, but this rod is perpendicular to the circular path because this rod forms a radial line on the circle, so it's perpendicular to the path that this thing follows at every point, so it does no work. There's no component of the tension force in the direction of motion. Does no work on the system. So the only force that does work on the system is the gravitational force. Now, in my notation, I say then that conservation of energy tells us that the initial kinetic plus the initial potential energy equals the final kinetic plus the final potential energy. If the initial point is at angle theta and the final point is at equilibrium, then this is going to give us the answer to our question. I do note that your book uses just K for kinetic energy and uses U for potential energy. Now that's a very common notation in physics, almost universal, K and U. I don't want to make you keep remembering what U means, so I keep writing PE. Okay. In any case, if this is true, provided only that the conservative forces do work. Okay, now we can draw a picture that represents the kinetic and potential energies. Okay, before the ball is being held stationary before being released, it has zero kinetic energy, so zero is going to be here. Okay, and it has a positive potential energy. Now, I haven't written the expression for the potential energy down. Potential energy, I say the change in potential energy is negative mgl times 1 minus cosine theta. There's a negative change in potential energy. So in order to draw this, I have to come over here and say, I'm going to declare that the final potential energy is zero. So if the potential energy here is zero and potential energy drops by this much, then your initial potential energy is positive, and of course equal to this thing without the negative sign. E is going to stand for the total energy, and I guess we ought to put a subscript on it. That's the initial, that's the final value of E. The total energy is the sum of kinetic and potential. So your initial E is the sum of the kinetic, which is zero, and the potential. It's equal to the potential energy. So I've got this line across here indicating that anything that comes up to this line is going to be equal to the initial potential energy. Okay, well, we have 4 bars on our bar graph that all have equal, that all come up to this line, so they all have to represent energy of this magnitude. So, why does the final kinetic energy equal the initial potential energy? Well, it's because the final potential energy is zero, and the total energy is kinetic plus potential, the total energy is equal to the initial potential because the initial kinetic energy is 0. And we conclude then that the initial kinetic energy, which added to the final, the final kinetic energy, which added to the final potential energy, has to equal the total energy. Because the force is conservative, total energy is the same before as it is after. So the kinetic here has to be equal to the original potential. You can also see this as an exchange. The potential energy goes from this much to 0. The kinetic energy goes from 0 to the same amount. Okay, again, total energy is conserved because your forces are conservative. All the forces that do work on the object are conservative. Sum of kinetic and potential is equal to the same thing here as it is here. If the kinetic is 0, then the potential is equal to the total energy. If the potential is equal, the kinetic is equal to the total energy. You need to understand that any way it can be said. And I just said it in a couple of different ways. We can get more specific. Here I've got the same diagram, but now I've got some quantities labeled. I say our initial potential energy is our mgl times the quantity 1 minus cosine theta. That parenthesis is closed, those parentheses are closed, but circle kind of obliterated that. Okay, so we have this for our initial potential energy. It has to be this because this is how much it loses as it goes from whatever it is here down to 0. And we declared the potential energy to be 0 at the equilibrium position. Okay, then everything else follows from what I just said. And we see that the total energy before release is mgl times 1 minus cosine theta. Total energy after release, because the forces are conservative, is mgl times 1 minus cosine theta. And the initial, or the final kinetic energy has to be mgl times 1 minus cosine theta. Now, if our goal is to figure out how fast the thing is moving at equilibrium, which is the original problem, we focus on the fact that the final kinetic energy is mgl times 1 minus cosine theta. And the final kinetic energy is 1/2 mvf squared. And every quantity in here except vf is assumed to be known. It was part of the diagram that I originally wrote. Or it's the universal gravitational constant, m for the mass, L for the length, theta for the angle. The only thing that wasn't in the original picture was final velocity, which is what we really want to find. So final velocity is unknown, everything else is given. We easily solve this for VF. Divide both sides by m, the m's go away, multiply both sides by 2, and we end up with 2gl times 1 minus cosine theta over here. 1 minus L times 1 minus cosine theta. And I got an extra L in that. What the hell am I doing? Okay, we have this. And that's what you get on the right hand side if you multiply by 2 over m. And then you have VF squared, so you take the square root. Now, I was a little careless when I solved this. It'd be plus or minus the square root. Okay. Although this is just, if you consider VF just to be the magnitude of the velocity, then you don't need the plus or minus. Magnitude is always positive. Okay. Now what do the bars look like if some other force that's not conservative does work on the system? And the example I gave, and I gave the example at the beginning, I've got this physical pendulum here, a couple of balls and a magnet attached to a strap. And if I release this thing from this point, it'll swing back to equilibrium and keep swinging back and forth. Now I'm actually helping it, because if I don't, and it swings back, it doesn't go that far past equilibrium because my fingers interfere with the motion. So the first case, where we have no non-conservative forces, kind of looks like this, although we don't have fingers helping it along. Okay, it's just swinging freely and there's nothing to get in the way. So if I have this on a good set of bearings up here, rotating about the good set of bearings, it'll work. It'll tend to oscillate the same distance on both sides. It'll keep oscillating for quite a while. Although there are still dissipative forces, it'll eventually lose its amplitude and come to rest. Another difference between this and the original situation, I keep pointing over there because that's where it was. In the original situation, this rod was massless. Okay, and this rod clearly isn't massless. It's actually got more mass probably than the magnet, but maybe only a quarter of the mass of the magnet and the balls added together. So you understand that that's the kind of situation. And what about a real world situation where we do have my fingers or air resistance or whatever doing work on the system as it moves? Okay. If the work is opposed to the direction of motion, and of course it doesn't have to be, my fingers could do the work and they could give it a good nudge here so it swings back much higher than it was. Maybe it swings back and goes around the pivot. But if we consider that negative work is done on the system, meaning that if the system's moving this way, the force is this way. It is opposite the direction of motion, so that your work done on the system is negative. Then what's the thing going to look like? Well, here's one possible case. Now in this case, I can actually do that. This thing just comes back to equilibrium and comes to rest there. So its initial kinetic energy is 0, its final kinetic energy is 0. How can that be? Well, because I exerted forces with my fingers that prevented it from swinging any further than equilibrium. The energy, the bar graphs in this case would look like this, the same as before. This is your initial state. And your final state looks like this. Everything is 0. Now I did insert this bar, and it's a downward bar because it's going below 0. It's work done by other forces. Maybe my fingers, maybe something else. Maybe you've got the thing in molasses and it just comes back to its equilibrium position and doesn't get any further. So this is not, this bar is not included in what your text does, but I thought it might be a good idea to include it here, showing that this work, or at least indicating maybe, that this work is equal and opposite to your initial potential energy, equal and opposite to your total energy. So this work, being equal and opposite to any other work that's done, is going to dissipate all your energy. And your final total energy is going to be 0. Okay. Now down here we do just a little bit with a couple of equations. I don't remember if your book gives you a formula in this form, but it follows immediately from what your book tells you. Of course, your book again uses K and U instead of KE and PE, but your book is going to tell you that the work done by the other is related to the initial and final kinetic and potential energies in a way that's consistent with this, that the work done by the other forces is equal to the change in kinetic plus the change in potential energies. Okay? In that case, if the kinetic energy, as in this case, is 0, okay, then the change in kinetic energy is 0. Final minus initial kinetic energy has to be 0. kinetic energy is zero at both before and after. Potential energy change is negative the initial potential energy. That's the final kinetic energy minus the initial, and we declared at the beginning that the final was zero, so that whatever the initial potential energy was, the negative of that initial potential energy is the change in potential energy. You can see that intuitively. Potential energy is this much, and now it's this much. The change is minus this. And that change is the work done by other forces. Okay, work done by other forces then, in Book's notation, it would be change in K plus change in U. That could be written in a number of ways. For example, the way I think it might be is work done by the other plus K naught plus U naught equals KF plus UF. And I think they actually use an I instead of a zero. Initial, I for initial, so I'm using a naught for the subscript. Your book would be using an I, but it says the same thing. Okay, I think you see this in your book, or in your ebook, or online. And of course, if I subtract these from both sides, I get a KF minus K naught, that's a delta K, or delta KE, and a UF minus U naught, which is the same as a change in potential energy. Okay, well, let's take a quick look at another situation. We've got a pendulum. Let's say it starts here. So this is initial, and over here is final. It's released from here, goes across here, and ends up at some final position. The position is going to be indicated by an angle alpha here with vertical, and an angle beta with vertical. Okay, well, we can use our diagrams, our bar graphs. Initially, the kinetic energy is zero, and it's got some potential energy. It's got some total energy. And then final, it's got no kinetic energy because it comes to rest over here again. And it's got a final potential energy. It's got a final total energy. If, in the absence of non-conservative forces, in other words, if all forces are conservative, and I didn't write that on the board, although it was stated, so let's say all forces are conservative, then there's no force that does work on the system, one way or the other. If no work is done on the system, then this W other is zero, and the sum of initial and final, the sum of initial kinetic and potential energies is equal to the sum of final kinetic and potential energies. Okay, well, if that's the case, since the initial and final kinetic energies from here to here are zero, this being the stopping point, then the total energy, which is your K naught plus U naught, is just equal to your initial potential energy. Only conservative forces act, so the final total energy has to equal the initial total energy. And it follows then that since the final kinetic energy is zero, and the total energy is the same as was here, which is equal to the initial potential energy, the final potential energy has to be equal to the final total energy, which is equal to the initial total energy, which is equal to the initial potential energy. So we conclude that final potential energy equals initial potential energy. Initial potential energy, as we saw, is mgl times 1 minus cosine of alpha. Now we were on this side in the previous picture, we're on this side in this picture. If the angle is the same and the length is the same, the drop is going to be the same. Okay, I guess my picture should include an L here, just to be sure we understand that. but it's pretty much implicit. I don't think it's really necessary. Okay, so potential energy here is mgl times 1 minus cosine alpha. It's equal, I'm sorry, that's this one, equal to this. And the final potential energy is mgl times 1 minus cosine beta. We can do the same analysis over here. Since the initial and final potential energies are equal, then this expression has to equal this expression. Well, the expressions are identical except for the alpha here and the beta here. We conclude that alpha equals beta, and we conclude from energy principles, not from any analysis of motion or anything, or experience, that as we would expect if we observe pendulums, the pendulum starts at an angle here, it ends at the same angle over here, in the absence of non-conservative forces, in the absence of non-gravitational forces. Okay, so there it is. Now, we're talking about absence of non-conservative forces and absence of non-gravitational forces. Another situation we want to take a quick look at. Get this thing so it's right side up. Here we have the same thing, a pendulum. We've got to have what I call a massless rigid rod here. Okay? And to that rod is attached a spring. It's attached to a wall someplace. And that spring is not just attached, but this thing is at a position where the spring has no tension. The spring is neither compressed nor extended. It's in its equilibrium, it's at its equilibrium length. So we have massless unstretched spring at the midpoint of the rod here. Let the spring constant be K. We ended up not using it, but generally you would have that. So the force exerted by the spring is negative Kx. The force exerted on the spring would be equal and opposite to that, of course. Okay, so as the pendulum swings back, what happens? Well, the spring gets compressed. Okay, the way I've got it written here, spring gets compressed. If the mass was on this side, the spring would get extended. Turns out it doesn't make any difference which, assuming you have only the conservative forces, the elastic conservative force exerted by the spring, it's an ideal spring, and the gravitational forces. We want to see how the gravitational and spring forces combine to govern how this thing, how this pendulum behaves. Okay, so as it swings back, the pendulum compresses. That increases the potential energy of the spring, because if you compress a spring, initially it's uncompressed. You attach a mass to the end of it and release it, nothing happens. If you compress the spring, put a mass on this end, the spring will then, if you release it, recoil, giving the mass a kinetic energy. Even if it's a massless spring. If it's not a massless spring, the spring picks up some kinetic energy. Different parts of the spring will be moving at different speeds, but you got if you add up the kinetic energies of all the particles and take those into account, if you've got a massive spring and a mass on the end of it, uncoil it, the total kinetic energy of all the particles in the spring and the mass add up to the potential energy, the work you did compressing the spring. Okay. So, in any case, as this thing swings back, then the potential energy of the spring increases because it gets progressively more and more compressed. Stores up more and more potential energy. Intuitively, it could now do work if it was released. Okay, now that means if you took the compressed spring away from this situation because the mass is compressing it, or the combination of all forces and torques is compressing it. If you took it away, it's compressed, it could do work. So it has positive potential energy. And I made another comment. By definition, the spring has done negative work in being compressed, because the spring is pushing this way, the compressing force is pushing this way. The spring's done negative work in being compressed, it has positive potential energy. Okay, well, as a pendulum swings back, its potential energy decreases. Okay, now this potential energy, this mass is going to decrease. It's going to go lower, and the potential energy of this spring, because the spring's being compressed, increases. Initially, the spring doesn't exert a lot of force because it's not compressed much, so it compresses very easily, and the mass will definitely start to move and compress the spring. Okay? Spring force continues to increase. So if it's a stiff enough spring, eventually it could happen that the force exerted by the spring here is sufficient to prevent the mass from moving all the way back to equilibrium. Now, if it's a lower force constant, the mass will move past equilibrium. But at some point, the spring will have stored up enough potential energy that the mass is going to stop moving and get pushed back to the original point. Now let's see how that looks on an energy diagram. So again, initially spring doesn't exert much force, so its potential energy doesn't increase very quickly, and that's what we really want to look at. So initially the potential energy loss of the mass is greater than the kinetic energy gain of the spring. And that's because the spring is pushing out, even with a small force, preventing the mass from swinging back as quickly as it otherwise would. Okay. A diagram, a graph. Now we're going to go to a graph here of potential energy versus angle. Okay, now really to analyze this graph you want potential energy versus position along the line. It's just a swing of an arc, it's a little complicated to do that. So there's some complications here in the way variables like distance along the arc and theta and the force of the pendulum don't align perfectly. So you're not going to get a totally rigorous analysis from these graphs, is what it amounts to, unless you are very good at figuring out the gravitational, or the spring, the elastic potential energy as a function of theta as opposed to length of the spring. Theta is not directly proportional to the length of the spring in this case, and that's really what I'm trying to say. Okay, putting aside all those little complications, just intuitively,